Welcome back as we continue our wonderful journey in core mathematics. My name is Nanayao Edu, and you can call me Nana. Remember to share this video, like this video, comment at the comment section, click on the notification bell, and subscribe to my YouTube channel so that you can get all videos on time. In our previous lesson, we have considered vectors, and we've looked at the introduction to vectors. We mentioned that for vectors, it's just a line that has a magnitude and a direction. Remember that anytime you move around, whatever you do, ensure that the mathematics you learn will have meaning with the things you do around you. So when you are looking around, when you are walking, when you are considering your steps, consider it in terms of vectors. In this lesson, we want to consider how we can find the magnitude of a vector. But then before we look at the magnitude of a vector, we want to consider vectors in 2D. So let's consider our vectors when we look at it in two-dimensional shape. So let's look at this image very carefully. When we see the image and we consider two dimension, basically when we look at two dimension, let's use a square to illustrate that. So we have our square here, not drawn to scale. So basically when we talk about a square, we know that all the sides are equal. So we say a square is in a two-dimensional shape because it doesn't have a form, right? It is not something you can touch and feel, right? So a two-dimensional shape, or 2D, where we call it a two-dimensional shape, basically represents having something that is in a flat form, right? Unlike where we have a three-dimensional face, where we have it, it could have a form. So it will have a form and you can probably be able to touch and feel it, right? So the television sets, the fridges that you have at home are three-dimensional, and then your calendar is a two-dimensional shape. So that is basically a two-dimensional shape. So we want to consider vectors when we look at them in a two-dimensional shape. So we are using the Cartesian plane, which is something we are familiar with. Basically, the Cartesian plane consists of representing lines or representing coordinates, representing the position of something when we are considering it in the x and y plane. So let's consider this vector. So the vector moves from the origin 0 and 0 and moves towards a point A and B. So let's label this vector as probably vector that begins from the point A, capital A, to the point capital B, right? So it means that when we are representing vectors in 2D, you realize that the length of the vector basically looks at moving from A to B, right? So we'll say that our vector AB, and we can represent vector with an AB with an arrow, right, indicating the direction, is equal to beginning from the OB, right, and then minus the OA. The reason is that basically, let's take it as you are moving from one point A to another point B, right? And let's assume that the point A is probably your 0. You are beginning from 0. And the way you move towards this side, you move towards your 10, right? If you want to find the length from A to B, or the vector from A to B, right, isn't it appropriate that you subtract A from B? So B minus A. Because when we have 10 minus 0, that gives us 10. And then it gives us the magnitude here, AB, which is right, 10 here, right? So that is why when we are representing vectors, resultantly, we say AB is OB minus OA. So, right, when we have AB, we can say that the OB in vector form is A and B, and then OA is our origin, which is 0 and 0. So A minus 0 will give us A, and then B minus 0 will give us B. So we see that our vector AB is our coordinates A and B, right? So that is how we represent our vector when we consider it in 2D form. Now let's move on and look at it when we are considering the magnitude or the length of a vector. So remember that when we were looking at the Pythagoras theorem, we said that once we have a right angle triangle, right, where you have a 90-degree, there's a special property. If this side is A, this side the length is B, and this length is C, we know that the square of C is equal to the sum of the square of the other side, A squared plus B squared, right? So representing vector in the Cartesian plane, as we see here, our x and our y, we know that the length from our origin here to the point here where the vector moves, right, on the Cartesian plane, we have represented it with A subscript x, right? And the point where it moves towards the y, which is from the point here to the top here, we see in the same direction, we represent it with A and y, right? So if you want to find the length, which is A represented here, it means that considering it in terms of the Pythagoras theorem, we can say that our A squared should be equal to the A subscript s squared, right, plus the A subscript y squared. So we can find the square root of both sides, which implies that this will cancel this, and we'll have our A to be equal to the square root of ax squared plus ay squared. Hence, our magnitude of a vector, which represents finding the length of a vector, right, or representing a vector in terms of the length, when we have our vector A, should be the square of what? A of x, so ax squared plus the square of A of y, so A subscript y all squared. The square roots of all that, right? So as we have indicated here. So that is how we can find the magnitude of a vector. Now let's consider this example. So the example says that consider that a vector A is represented by the line segment which goes from the point 2, 3 to the point 4, 8. Calculate the components and the length of the vector. So let's consider how we can calculate that. So basically, let's represent this in a Cartesian plane. So we can have our Cartesian plane. They are all positive values, so we'll consider them in the positive plane, right? So we know that we have our x here, we have our y here, right? So our s can move from 1 to 2 to 3 to 4. Our highest value of x is probably our 4. And the highest value of y is 8. So we can have a scale where we have 2, we have 4, we have 6, and then we have 8, right? So there are in-betweens. So we can have a 1 here, a 3, a 5, and then a 7, right? Now let's plot the point. The first point is 2. So 2 on the x-axis, 3 on the y-axis. So that is a point here, right? Let's give it a label as x. So x is 2 and 3. And then we have another point 4 and 8. So we know that our 4 is here, right? So 4 on the x-axis, 8 on the y-axis. So somewhere here, right? So we can call it y. So 4 to 8. So we can draw a line. And then we have our direction. Then this is a vector, right? So when we are looking at the vector can actually we can look at it in terms of the x coordinates, where we move from this side, right, towards our 4 here, and then we move up towards our y. So in this direction, and then towards the top here. So we can see that our vector, the x coordinate of our vector, if you want to look at it here in terms of the line or the geometry, then we can consider it as moving from the 2 here to the 4 here, right? So from 2 to 4, what's the distance? So we have 1 and 2. So x is 2 here. Then when we consider it here, we are looking at it moving from the 3 here to our 8, right? So it moves from the 3 to the 8. So when we look at the distance here from 3 to 8, the distance of y should be 5, right? So in terms of vectors, we know that if we have x and y, from what we have learned previously, if you have x and y as a vector, it means that we have oy minus ox. And we've explained this in our previous lesson. So basically, oy minus ox. Now we know that our x, right, as a coordinate is our 2 and 3, and then our y as a coordinate is our 4 and 8. So we can write our x and y as a vector to be equal to oy. So let's write oy in terms of vector. So our 4, which is our x part, will be at the top, and our 8, which is our y part, will be down, right? Minus ox. So ox is 2 and then 3. So let's see if it gives us the same values as our x and y where we looked at it in the coordinates. So 4 minus 2 should give us 2, and then 8 minus 3 should give us 5, right? So the first part of the question, which is asking us to find the component, we have seen it as what? 2 on the x-axis and 5 on the y-axis, right? And then now we want to find the magnitude. So the magnitude, x and y, we put 2 lines by them to represent the magnitude. We know that that should be the square root of the x component and the y component. So x squared plus y squared, the squares of them. So based on the Pythagoras theorem that we looked at. So it means that our xy as a magnitude should be equal to the square root of 2 squared plus 5 all squared. So x and y, finding the magnitude, 2 squared should give us 4, and then 5 squared should give us 25, right? So it means that x and y as a magnitude should be equal to the square root of 29. Now, square root of 29, you can't change it in terms of sets, so we must leave our magnitude to be equal to the square root of 29. We can add a unit to it, right? 29 units. Unit means that it's a length. So in this lesson, we have basically considered the magnitude of a vector, and we've looked at it using the Cartesian plane, where we've considered the question and gone through it to be able to determine how we can find the magnitude of a vector.